Right now, somewhere over the Pacific, a storm wider than the state of Texas is spinning up. In one single day, its winds can jump by 35 miles an hour. That is the moment forecasters dread. They call it rapid intensification, and it can turn a gentle rain into a monster overnight. We're going to climb inside these giants. You will stand in the calm eye where you can see the stars. You will meet a wall of water taller than a 2-story house. You will watch the strongest storm ever to hit land tear an island apart, and you will find out why the ocean is building bigger monsters every single year. If storms like this grip you, tap like and subscribe so you never miss what comes next. Take a breath. We begin. On a warm morning in a small fishing town, the sea looks like a sheet of glass. Boats rock in the harbour, children kick a ball down a sandy street, a fisherman checks his nets and squints at the sky. Nothing up there looks wrong, yet hundreds of miles out over the open ocean, something has already begun. The story starts with water. Warm water. Out in the tropics, near the middle of the planet, the sun beats straight down on the sea for months. It heats the top layer of the ocean the way a stove heats a pot. By late summer, that water can climb past 80 degrees Fahrenheit. Warm bath water, spread across an area bigger than a dozen states. That warmth is the key to everything that follows. Storms are picky. They need the ocean to be at least 80 degrees. They need it warm at the surface and warm far below, many feet down. When those things line up, the sea becomes a giant tank of fuel, just sitting there, waiting. Here is the strange part. A super typhoon does not arrive as a super typhoon. It begins as almost nothing. A loose clump of thunderstorms, a patch of grey cloud with no shape, no spin, no name. Ships sail right past it, satellites barely notice. If you flew over it in a plane, you might call it a rainy afternoon and move on. But that clump is sitting on top of the fuel tank, and the ocean is about to hand it a match. Warm water does not stay put. It rises up as invisible steam into the air above the storm. Picture the lid on a pot of boiling water, and the way steam gathers underneath. That rising steam carries heat with it, packed inside like energy stored in a battery. As it climbs, it cools, forms clouds, and pours that heat back into the storm. The heat makes the air rise faster. Faster rising air pulls in more warm, wet air from below. More wet air means more steam, more heat, more rising. Round and round it goes, feeding itself. Scientists have a simple name for what this clump is becoming: a heat engine. Same idea as the engine in a car, except the fuel is a warm ocean and the exhaust is wind and rain. As long as the sea stays hot, the engine keeps running. It can run for a week, it can cross thousands of miles of water, and every hour it runs, it grows a little bigger and a little angrier. Back in the fishing town, the sky's still blue. The fisherman finishes with his nets, the children keep playing. The radio mentions a weak system far away, probably nothing. That word probably is doing a lot of work, because far out at sea, over water as warm as a bath and deeper than most people picture, the clump has started to turn, slowly at first. A lazy swirl in the clouds, the first hint of a spin that will one day grow strong enough to flatten a city. To understand how a rainy afternoon becomes a monster, we have to look closer at that fuel, and it turns out the ocean is hiding far more of it than anyone can see from a boat. The ocean looks the same all the way down, but that is a trick your eyes are playing on you. From a boat, the sea is just a blue surface, flat, simple. Underneath, though, the water is stacked in layers, like a cake. The top layer, warmed by the sun, floats on top of colder, heavier water below. And the depth of that warm layer decides whether a storm lives or dies. Here is why. A weak storm churns the sea beneath it. Its winds drag on the surface and stir the water like a spoon in a cup. If the warm layer is thin, that stirring pulls cold water up from below. Cold water starves the engine. The steam stops rising. The storm chokes on its own mess and fades. Many baby storms die exactly this way, and no one ever hears their names. Sometimes, though, the warm layer runs deep. Really deep. Scientists measure this with a mouthful of a term, ocean heat content, which is a fancy way of asking one question. How much warm water is stored below the surface, ready to burn? When that number is high, the storm can stir all it wants and still find nothing but more warm water underneath. The stirring brings up more fuel instead of less. Think of it like a campfire. A thin warm layer is a handful of twigs. It flares up bright, then dies in minutes. A deep warm layer is a stack of dry logs. Once it catches, it burns for hours, and it is very hard to put out. This year, in the Western Pacific, the logs are stacked high. Large stretches of ocean have been sitting at 85 degrees Fahrenheit and warmer, with heat reaching far below the surface. That is why forecasters have been so tense. The tank is full, and the tank is huge. Now watch what all that heat does. As warm, wet air spirals into the center of the storm and rises, the water vapor inside it turns back into liquid, forming clouds. That change releases the heat it was carrying. This is the secret of the whole machine. The heat was hidden inside the water the entire time, and the storm unlocks it high in the sky. The amount of energy is hard to picture. A single mature typhoon can release more heat energy in one day than the entire United States uses in electricity in a year, and it does that again the next day, and the next, for days on end. That is the size of the beast we're talking about. The engine has a cruel design feature. The more heat it releases, the lower the air pressure drops at its center. Lower pressure sucks in wind harder from all around. Harder wind whips up more sea spray and steam. More steam means more heat, which drops the pressure even lower. The storm is now pushing on its own gas pedal. Left alone over deep, warm water, this loop has no natural brake inside it. The engine just keeps revving. Faster, tighter, stronger. The only thing that can stop it now must come from the outside, and something usually does. High above the storm, a hidden force is waiting, one that has torn apart thousands of storms before they ever had a chance. Most clumps of thunderstorms never survive their first meeting with it. The question is whether this one will. High above the storm, where planes fly, the winds have their own plans. Down at the surface, the young storm is spinning nicely. But a tropical cyclone is a tall thing. From the sea to the top of its clouds, it stands around 10 miles high. That is taller than any mountain on Earth, a stack of cloud reaching up past where jets cruise. For the storm to grow, that entire tower has to stay lined up, stacked straight like a spinning top. Here is the problem. The wind at the bottom of the tower and the wind at the top are often moving in different directions at different speeds. Forecasters call this wind shear. Picture a tall stack of pancakes with someone pushing the top ones one way and the bottom ones another. The stack leans, then it smears sideways, then it falls apart. Wind shear does the same thing to a storm. Strong high winds grab the top of the tower and drag it away from the base. The engine can no longer stack its heat straight up. The warm rising core gets tilted and blown off to one side, the clouds shred, the spin loosens. Within a day, a promising storm can be reduced to a smear of harmless rain. This is the break the whole system was missing, and most of the time, it works. On any given day over the tropics, dozens of little storm clumps are trying to organize, and wind shear knocks most of them flat before they ever earn a name. It is the ocean's fuel against the sky's scissors, and usually the scissors win. Which brings us to the nightmare setup. Every so often the sky goes quiet, the high winds die down, the shear drops to almost nothing, calm and steady from top to bottom. When that happens over deep warm water, the brake is gone, the scissors are put away, and the engine is free to run at full power with nothing to stop it. Forecasters have a word for that combination, and it makes them lose sleep. A window, a stretch of ocean and sky where every ingredient lines up at once. Deep warm water below, calm winds above, moist air all around. When a storm finds a window like that, it explodes into life. Fast, violent. This is exactly what happened earlier this year with a storm named Barbie. It rolled over water near 90 degrees Fahrenheit, with the high winds above it lying flat and weak. The brake was gone. With nothing holding it back, Barbie was free to organize and spin up into one of the strongest storms of the season. And here is the part that should make you sit up. Right now, over the Western Pacific, these calm windows are opening more often than they used to. Warmer oceans and shifting wind patterns are handing storms more of these free runs, more chances to hit the gas with no brake in sight. So the fuel is loaded, the brake is off. The clump of clouds has everything it needs, now it just needs to become a machine. And the moment it does, the moment that loose, wobbly spin snaps into something with a center and a shape, everything changes. because that is when the eye is born and the storm stops being a weather event and starts being a weapon. The moment a storm becomes a killer has a look, and from space you can see it happen. For hours, maybe days, the clump has been a messy swirl, ragged clouds, a loose, wobbly spin, no real centre. Then, over deep warm water with calm winds above, the pieces click together. The spin tightens. The clouds pull inward, wrapping around a single point like water circling a drain, and right at the heart of it, a small dark hole opens in the cloud tops. That hole is the eye, and when the eye appears, forecasters know the storm has crossed a line. Up to this point, the winds have been building. Once they hold at 74 miles an hour, this system earns a new title. In the Western Pacific, they call it a typhoon. In the Atlantic Ocean, the very same storm would be called a hurricane. Same beast, different name, depending on which part of the world it is tearing through. Reaching typhoon strength means the storm has finished building itself. It now has a working core, spiral arms of rain wrapping outward, and tall walls of cloud around a calm centre. It has become a self-running machine, and it no longer needs luck to survive. As long as it stays over warm water, it feeds itself and holds together. Picture a figure skater spinning on the ice. She starts with her arms stretched out, turning slowly. Then she pulls her arms in tight against her body. Suddenly she whips around far faster, all that motion squeezed into a smaller space. A storm does the same trick. As the winds pull in toward the centre, they speed up, tighter and faster, until the core is howling. Now the storm has real structure, and every part has a job. The outer rain bands sweep in moisture and feed the core. The centre draws everything inward and down, and around that centre rises a ring of the tallest, meanest clouds in the whole system, the part that does the real damage. This is also the moment the storm becomes predictable enough to name and track, and dangerous enough to fear. Warning centres start drawing its path across the map. Coastal towns days ahead begin to appear inside the danger zone. The machine has switched on, and now it is coming for someone. Here is what makes forecasters uneasy at this stage. A storm that has just organised is a storm ready to grow. All its parts are in place. The engine is warm. If it stays over deep, hot water with calm winds above, there is nothing to stop it from getting stronger. Much stronger. And fast. Most storms take their time. They strengthen over days, giving people on the coast plenty of warning to board up windows and drive inland. That slow, steady climb is what forecasters count on. It is the difference between a hard day and a disaster. But every so often, a freshly formed storm does something that breaks the rules. Instead of climbing slowly, it detonates. Its winds leap upward in a single day, turning a manageable storm into a monster before anyone on the coast has finished packing. Forecasters have a name for this. It is the thing they fear most in the whole science of storms, and once it starts, the clock starts ticking against everyone in its path. There is a number that makes a room full of forecasters go silent. That number is 35. When a storm's top winds jump by at least 35 miles an hour in a single day, scientists give it a name: rapid intensification. It sounds technical and dull. In real life, it is one of the most frightening things a storm can do. Here is why 35 in a day is such a big deal. Picture a car on a highway. Speeding up by 35 miles an hour over a whole afternoon is normal. Doing it in a few seconds throws you back in your seat. A storm doing it in a day is that violent jump, except the storm keeps going and going. Some do not stop at 35. Take a storm named Chantu, back in 2021. It started as a weak swirl with winds around 30 miles an hour, the kind of thing you would barely notice. Under 2 days later, its winds had screamed up to 160 miles an hour. A gentle breeze had become a Category 5 monster in less time than a weekend. Only a handful of storms in all of recorded history have ever strengthened that fast. This year gave us another one, Bavi. Its winds surged roughly 75 miles an hour in a single day, and about 100 miles an hour over a day and a half. And Dolphin, the storm that just raked past Japan and slammed into China, went from a weak tropical storm to a full super typhoon in barely 2 days. Textbook cases, forecasters called them. Textbook, and terrifying. So what flips the switch? All the ingredients we have already met arriving at once. Deep warm water below, calm winds above, moist air packed all around. When a storm rolls into a patch of ocean where everything lines up, the engine stops idling and floors it. The pressure at the centre crashes, wind rushes in harder. That wind whips up more steam, which drops the pressure further, which pulls in even harder wind. The loop spins faster and faster, and the storm feeds on its own fury. The strength frightens people. The speed is what kills them. A storm that was a nuisance yesterday can be a life-ending threat by tomorrow morning. Imagine going to sleep with a weak rainstorm offshore and waking up to a wall of destruction bearing down on your town. Families who plan to leave in the morning wake up to find the roads already flooding, and here is the trend that keeps scientists up at night. Rapid intensification used to be rare. Now it is happening about 3 times more often than it did decades ago. Warmer, deeper ocean heat is feeding storms more fuel than ever, and more of them are making that violent leap. The monster keeps getting bigger, and it is learning to appear out of nowhere. For the people on the coast, everything depends on one thing: warning. If forecasters can see the leap coming, towns can empty out in time. If they cannot, thousands of people are still asleep when the water arrives. Which raises the most important question in this whole story. Can we predict it? Can anyone look at a weak storm and know it is about to explode? The answer is the reason forecasters are so worried, and it is stranger than you would think. Forecasters can tell you where a storm will go 3 days from now within a few miles. Ask them how strong it will be, and they start to sweat. This is the great embarrassment of storm science. Over the last few decades, tracking has gotten remarkably good. The path a storm takes, drawn as a line across the ocean, is now predicted with real skill. But intensity, how hard the winds will actually blow, has stayed stubbornly hard to pin down. And the hardest part of all is that sudden violent leap, the rapid intensification we just met. Why is it so tough? Because the leap is born deep inside the storm, in a place too small and too chaotic for our tools to see clearly. The path of a storm is steered by big, slow features, giant ridges of high pressure that push it along like a leaf in a stream. Those are easy to spot from far away. The strength, though, is decided in the tight little core around the eye, where things change minute by minute. Picture trying to predict which log in a campfire will suddenly flare up and shoot sparks. The fire follows rules, but the exact moment and spot of the flare-up depends on tiny details: a pocket of dry wood, a gust of air, a shift you could never measure in time. A storm's core is like that, only miles wide and spinning at highway speeds. It gets worse. Scientists recently discovered that rapid intensification happens in more than one way. There are at least 2 completely different flavors of it, each with its own recipe and its own triggers. A team studying storms on powerful computers found that even a lopsided, messy storm, the kind you would bet against, can still find a path to explode. So a forecaster cannot simply memorize one warning sign. The storm has more than one way to surprise them. All of this makes the leap fiendishly hard to call, and the cost of getting it wrong is measured in lives. When a forecast says a storm will come ashore as a moderate one, people prepare for a moderate one. If it instead explodes overnight into a giant, those same people are caught flat, with boarded windows meant for a smaller beast and evacuation plans that suddenly move too slowly. That is why the rapid leap sits at the centre of the whole problem. The strongest storms, the ones that flatten cities, are very often the ones that leapt at the last minute. And those same storms carry the biggest forecast errors of all. The deadliest storms and the hardest to predict are the same storms. That overlap is a scientist's worst nightmare. So teams around the world have thrown everything at the problem. In China, forecasters recently switched on a brand new system built to predict the leap up to a full day ahead, one of the top scientific puzzles their country decided to attack. Around the world, meteorologists are feeding storms into powerful computers, hunting for the hidden signals that come just before the explosion. They are getting better, slowly. But the ocean keeps changing the game, warming up, feeding the storms, making the leaps more common and more violent than the record books ever prepared us for. To really understand what makes these storms so deadly, we have to go inside one, past the outer rain, into the ring of cloud where the winds are fastest and the danger is greatest, into the part of the storm that does the killing, If you could fly straight into a super typhoon, the outer edge would almost fool you. At first, the rain bands feel like an ordinary storm. Heavy rain, gusty wind, bursts of downpour with calmer gaps in between. You might think you have seen worse. Then, closer to the centre, the calm gaps vanish. The rain turns solid. The wind stops gusting and starts screaming, a steady roar that never lets up. You have reached the eye wall. The eye wall is the ring of towering clouds that circles the eye, and it is the most violent place in the entire storm. This is the engine room. Here the winds hit their absolute peak. Here the rain comes down hardest. Everything the storm can do to hurt you, it does in this ring. How tall is it? The eye wall stands about 10 miles high, a wall of cloud reaching up past where airliners fly. Imagine a circular skyscraper made of screaming wind and rain, taller than 18 Empire State Buildings stacked on top of each other, wrapped in a ring dozens of miles across. And every bit of it is spinning. Why is this ring so much worse than the rest? It comes down to pressure. At the storm's centre, the air pressure is incredibly low, lower than anywhere else on the planet's surface. Just outside, the pressure is normal. Air always rushes from high pressure toward low, and the bigger the gap, the harder it rushes. In a super typhoon, that gap is enormous and squeezed into a tight ring, so the wind pouring across it moves at a savage speed. Think of letting go of a blown-up balloon. The air trapped inside is at higher pressure than the room, so it blasts out the neck and sends the balloon zipping around wildly. A storm's eye wall is that same rush of air toward low pressure, except it never runs out, because the ocean keeps refilling it. Inside the eye wall, warm, wet air blows sideways and also shoots upward, racing to the top of the storm at the speed of an elevator in a tall building. That rising air is what releases all the stored heat, powering the whole machine. The eye wall is where the fuel actually burns. It is the firebox of the engine. This is the part of the storm that peels roofs off houses, that snaps concrete power poles like dry twigs, that turns a loose piece of sheet metal into a flying blade. When people describe a super typhoon sounding like a freight train parked on top of their house, refusing to leave, they are describing the eye wall passing over them, and it moves slowly. In a big, slow storm, the eye wall can take an hour or more to grind across a single town. 60 minutes of the strongest wind on Earth, hour after hour of pure force, with debris flying and the roar never stopping. For many coastal families, surviving a super typhoon means surviving that 1 hour. Then, strangely, it all stops. The wind dies, the rain quits, the roar fades to silence, and a patch of blue sky slides overhead. Survivors step outside, sure the storm has passed and the worst is over. They're about to make the most dangerous mistake of their lives. Because the calm they are standing in has a name, and it is one of the greatest tricks in all of nature. The deadliest place in a super typhoon is the one place that looks completely safe. After the eye wall's hour of fury, the world goes quiet. The wind drops to a breeze, the rain stops. Overhead, the clouds part into a ragged circle, and sunlight, or at night, actual stars pours through. The air feels warm and still. To anyone who just survived the eye wall, it feels like a miracle. It feels like the end. This calm circle is the eye of the storm, and understanding why it is calm tells you why it is so dangerous. Remember that inside the eye wall, air is racing upward at tremendous speed. But at the very centre, the opposite happens. Some of that air sinks back down, slowly, right through the middle. Sinking air is dry, clear air. It smothers clouds and rain. That is why the eye stays calm and bright while a wall of chaos spins just a few miles away. The eye is usually a rough circle, often 20 to 40 miles across, though some grow much wider, and a few shrink to just a couple of miles. The tighter and rounder the eye, the stronger the storm tends to be. Pilots who fly into these storms describe the biggest eyes as standing inside a vast stadium, with cloud walls rising 10 miles tall on every side and calm blue directly overhead. A cathedral of cloud, silent at the centre of the loudest place on Earth. The sinking air holds another secret. It is warm. Down inside the eye, the air can be several degrees warmer than the storm around it, and high up, miles above your head, it can be more than 15 degrees warmer than the air outside the eye. That warm core is the true heart of the engine. The warmer the core runs, the lower the pressure drops, and the harder those eyewall winds blow. In a strange way, the peaceful eye is the throne room of the whole monster. Now here is the trap. The eye is just the middle. It is a hole passing over you, and it has two sides. When the front eyewall finishes and the calm arrives, the back eyewall is still coming. It sits on the far side of that quiet circle, spinning just as hard, and it is heading straight for you next. This is why the eye has killed so many people. Families who huddled through the first eyewall step outside during the calm. Thinking the storm is finished, they start to clean up. They cross the street to check on a neighbour. They let their guard down. Then, sometimes in only a few minutes, the far wall arrives with no warning, and the wind returns to full strength from the opposite direction. People caught in the open have almost no chance. Even worse, the returning wind often blows against the wreckage the first wall created. Roofs already loosened get ripped free, trees already leaning finally fall. Water already piled up gets shoved a new way. The second half of a super typhoon can be more deadly than the first, striking a place that is already broken. So the calm is a lie the storm tells you. A quiet, sunlit, warm-hearted lie, wrapped inside the fiercest weather on the planet. By now you have felt what one of these storms can do, but we still have not said the words that separate an ordinary typhoon from the true giants. What exactly makes a typhoon a super typhoon? The line is sharper and scarier than you might guess. Every typhoon is dangerous, but a small handful cross a line into a different league entirely. We have been using the word super typhoon since the start, and it is time to say exactly what they mean. Storms get sorted by one thing above all others: the top speed of their steady winds, the wind that holds strong minute after minute, ignoring the single lucky gust. That number decides everything about how a storm is ranked. A storm becomes a plain typhoon once those steady winds reach 74 miles an hour. That already means torn roofs and downed trees, but the scale keeps climbing. As the winds rise into the low hundreds of miles an hour, the storm grows from dangerous to devastating. And then, at 150 miles an hour of sustained wind, forecasters reach for a special label: Super Typhoon, 150 miles an hour. Hold that number for a second. That is faster than almost any car you will ever ride in, blowing steadily, for hours, across whole towns. At that speed, wind stops being weather and becomes a physical force, a wall of moving air strong enough to push over trucks and collapse buildings. To picture the jump, think about the difference between highway driving and the launch of a roller coaster. A regular typhoon is highway speed, fast and serious. A super typhoon is the roller coaster drop, a force that presses you into your seat and steals your breath. The gap between them is huge. The strongest super typhoons carry several times the destructive punch of a storm that barely earns the name. Here is the part most people do not realize. Wind damage climbs far faster than the wind speed itself. Double the wind and the damage multiplies many times over. The force that wind pushes with grows sharply as it speeds up. So a storm at 150 miles an hour is vastly more destructive than one at 100, even though the numbers look close on paper. Every extra bit of speed lands with brutal growing weight. That is why forecasters treat the super typhoon label with such dread. When a storm crosses that line, they stop thinking about damaged rooftops and start thinking about flattened neighborhoods, about whole towns wiped clean, about the kind of destruction that shows up from space. And a rare few climb even higher, into the very top rank that storm scientists recognize, the same top rank as the worst hurricanes that have ever struck the United States. These are the storms that make history, the ones with names people never forget. This year alone, the Western Pacific has already produced several of them, one after another, in a season running far hotter than normal. There is one more thing hidden in the label. A super typhoon at sea and a super typhoon at the coast are different threats. Many reach their peak strength over open water, then weaken a little before they hit land, sparing the people in their path the very worst. The true nightmare is a storm that holds its full super typhoon power all the way to the shore, hammering a coastline at its absolute peak. Only a handful of storms in history have managed that, and the most famous of them all struck one November morning with winds so strong they set a record that still stands. To understand what a super typhoon can truly do, we have to meet it. The wind gets all the attention, but the ocean itself is what does most of the killing. Ask people what a super typhoon does, and they picture wind, flying roofs, bent trees, howling gusts. Yet across history, the single deadliest thing these storms bring is water, shoved ashore in a way that catches people completely off guard. It is called storm surge, and it drowns more victims than the wind ever touches. So what is storm surge? Picture the storm as a giant hand pressing down and pushing across the sea. Its fierce winds shove on the surface of the ocean for hundreds of miles, piling water up ahead of the storm like snow in front of a plough. As the storm nears the coast, that mountain of piled up water has nowhere to go but up and over the land. The sea comes in fast, it surges, rising many feet in minutes and rolling inland like a fast, dirty flood, and this is a lot of water. In the worst storms, the surge can lift the sea more than 20 feet above its normal level. 20 feet is a 2-story house. Imagine the ocean suddenly standing as tall as the roof of your home, then charging inland faster than you can run. That is what a storm surge is. People underestimate it because it looks tame at first. The water simply keeps rising and rising, higher than anyone expected, filling streets and homes and swallowing cars. In the dark, in the wind, families climb to their roofs and find the water still climbing after them. Here is the cruel physics behind it. Water is heavy. Astonishingly heavy. A single cubic yard of seawater weighs about as much as a small car. So when a wall of water moves inland, it is like a fleet of cars driving through your living room, then draining back out and dragging everything with it. Buildings that survive the wind get knocked flat by the weight and force of the moving sea. The surge also arrives at the worst possible moment, right as the eye wall comes ashore, when the wind is already at its most deadly. So people face 2 killers at once, screaming wind above, rising water below, both at full strength in the same terrible hour. And the height of the surge depends on more than the storm's strength. It depends on the shape of the land it hits. A deep, steep coastline lets the water slide back off, but a shallow, gently sloping seafloor lets the storm pile the water higher and drive it farther inland. On flat coasts, a surge can push water more than half a mile past the shoreline, turning whole neighbourhoods into open sea. This is why forecasters often fear the water more than the wind. Wind damage is brutal, yet people mostly survive it indoors. Storm surge fills those same indoor spaces with ocean. The safest room in the house becomes a trap once the water pours under the door and keeps climbing toward the ceiling. There is one thing that makes a surge far worse than all of this. One feature of certain coastlines that can turn a bad surge into an unstoppable one. It has to do with the exact shape of a bay. And the most heartbreaking example in modern history happened in a place shaped like a funnel, pointed straight at a sleeping city. Some coastlines are shaped like a trap, and the water knows exactly how to use them. We just saw that a shallow, gentle seafloor makes a storm surge worse. But there is one shape of coast that turns a dangerous surge into a monstrous one. A bay that narrows as it goes inland. A funnel. Think about how a funnel works in your kitchen. You pour liquid into the wide top, and it comes rushing out the narrow bottom faster and higher than it went in. All that water gets squeezed into a smaller and smaller space, so it has nowhere to go but up. A funnel-shaped bay does the exact same thing to a storm surge on a terrifying scale. Here is how the trap springs. The storm pushes a huge mound of seawater toward the coast. That water enters the wide mouth of the bay. As the bay narrows, the same enormous volume of water gets crammed into a tighter and tighter channel. With nowhere left to spread out sideways, the water climbs and climbs. A surge that might have been 10 feet on an open coast can rear up far higher at the pointed end of a funnel, right where the land pinches shut. Now add one more cruel detail. People build cities in exactly these spots. Sheltered bays make calm harbours, good for boats and trade. So towns grow up at the narrow, protected end of the funnel, the safest place in normal weather and the deadliest place in a storm. The very shape that makes a lovely harbour is the shape that concentrates a surge into a killing blow. The most haunting example in modern memory is a bay in the central Philippines near a city called Tacloban. The coastline there forms a long, narrowing gulf that points like an arrow straight at the city. For generations, it gave fishermen calm waters and safe harbour. Then, on one November morning, A super typhoon drove the sea into that funnel, and the Gulf did what funnels do. It took a massive surge and squeezed it even higher, aiming the concentrated force of the ocean directly at hundreds of thousands of sleeping people. The water rose faster than anyone believed possible. Whole districts that sat only a few feet above sea level vanished under the flood within minutes. People who had braced for wind found the ocean itself pouring through their streets, higher than their homes. And here is the part that stings the most. The danger was known. Scientists had run the numbers and predicted a huge surge 2 full days ahead. Warnings went out over the radio the night before, but the word storm surge did not land the way they needed to. Many families had lived through fierce winds before and stayed put, picturing another rough but survivable night. The sea climbing above their rooftops was something they could not imagine. That gap between a warning given and a warning understood is one of the hardest problems in this entire field. You can predict the water perfectly and still lose people if they do not grasp what is coming. A funnel-shaped bay gives you less room for that mistake than almost anywhere on Earth. The storm that filled that funnel was no ordinary typhoon. It came ashore as possibly the strongest storm ever to hit land in recorded history, with winds that still hold a grim record today. To understand what these giants are truly capable of, we have to look straight at it. On the 8th of November, in 2013, the strongest storm ever measured at landfall came ashore, and the world learned a new kind of fear. Its name was Haiyan. In the Philippines, people called it Yolanda. Days earlier, it had been an ordinary patch of low pressure far out in the Pacific, thousands of miles from land. Then it found deep, warm water and calm skies above, and it began the violent climb we have been tracking through this whole story. A tropical depression, a tropical storm, a typhoon. Then something the record books had barely seen. By the time Haiyan reached the central Philippines, forecasters put its steady winds at around 195 miles an hour, with gusts howling even higher. Sit with that number, 195 miles an hour of sustained wind, holding steady as the storm slammed into inhabited islands. That is faster than a race car screaming down a straightaway, except this was a wall of wind that wide, grinding across whole towns. This set a chilling record. Haiyan is widely counted as the strongest tropical cyclone ever to make landfall in recorded history, tied at the very top with only 1 or 2 others. Most storms this powerful reach their peak far out at sea and weaken before they touch land. Haiyan did the opposite. It arrived at nearly its full monstrous strength, hitting the coast at its worst. The storm was also enormous. From edge to edge, Haiyan spanned around 370 miles, wide enough to blanket an entire chain of islands at once. Its cloud shield covered an area of land about the size of the country of Portugal. There was no dodging it, no gap to slip through. For the islands in its path, the whole sky was the storm. What does 195 miles an hour actually do? It stops being wind in any normal sense. At that speed, the air itself becomes a solid force. It tears the roofs off concrete buildings and sends them spinning away like playing cards. It snaps sturdy coconut palms in half and strips others down to bare poles. It picks up trucks, boats and slabs of metal and hurls them through the air as deadly missiles. Anything left outside becomes a weapon. Survivors described a sound like a jet engine that would not stop, a roar so total it drowned out screaming just a few feet away. They described the air filling with flying debris until they could see almost nothing. They described holding on to anything bolted down and praying it would hold. For hour after hour, the eye wall of Haiyan ground across the islands, with the strongest wind ever recorded striking land. And through all of that, the wind was only the opening act. As terrifying as 195 miles an hour was, it accounted for only a fraction of the people who died that morning. The true killer was still on its way, driven ahead of the wind, funneled by the shape of the coast we just explored. Because Haiyan was aiming its full fury straight at that narrowing gulf, straight at the city of Tacloban, and straight at a wall of water that few of the people in its path could even imagine. What happened when the sea reached the city is the darkest chapter in this whole story, and it is the reason the world will never forget the name Haiyan. The people of Tacloban braced for a terrible wind, and the sea came for them instead. Tacloban was a busy coastal city of more than 200,000 people, sitting at the pointed end of that funnel-shaped gulf. On the morning of the 8th, as Haiyan's eye wall roared in, Families hunkered down against the wind exactly as they had in storms before. Then, in the middle of the chaos, the water began to rise. It kept coming, far past where stormwater usually stops. Witnesses watched the sea climb the walls of their homes, past their knees, past their waists, past the windows. Driven by the strongest winds ever to strike land, and squeezed higher by the narrowing gulf, the surge rose to somewhere around 17 to 24 feet in the worst-hit areas. The ocean stood as tall as a 2-story building and poured through the streets of a sleeping city. People scrambled upward. They climbed onto tables, then onto roofs, then into the tops of trees, with the black water chasing them the whole way. Whole families were swept out of their houses. Cars floated down streets. Ships were lifted clean out of the harbour and dropped onto neighbourhoods blocks inland, crushing homes beneath them. The flood carried a battering ram of debris, splintered wood and twisted metal, and everything the wind had already torn loose. When the water finally pulled back, it dragged much of the city out to sea with it. Streets that had held homes and shops were scraped down to mud and rubble, and the human cost was almost too large to hold in your mind. Across the Philippines, Haiyan left more than 6,000 people dead, over 1,000 more missing, and tens of thousands injured. For weeks afterward, bodies were still being found in the wreckage. The vast majority of those deaths came from the water, the storm surge, that same rising sea that so many had failed to picture when the warnings came. Wind killed some, the ocean killed far more. What makes it heartbreaking is that the surge had been predicted. 2 days ahead, scientists had modelled it and warned that a massive wall of water was coming. The information was correct and it was early. But the warning ran into a wall of its own. The simple human trouble of imagining something you've never seen. A city that had survived many big winds struggled to picture the ocean itself rising 2 stories high and marching through downtown. Haiyan changed how the world talks about these storms. Afterward, forecasters worked hard to make the words storm, surge carry the weight they deserved, describing the danger in feet of water and in plain, frightening pictures instead of calm, technical terms. Coastal towns redrew their maps. Governments marked no-build zones along the shore and tried to move families to higher ground. Yet the deeper lesson of Tacloban still hangs over every forecaster today. You can see the monster coming. You can measure it, predict it, and shout the warning. And people can still be lost simply because the size of the threat is beyond what they have ever lived through. Against a storm like Haiyan, knowledge alone struggled to save everyone. Haiyan struck with wind and water together, but some super typhoons carry a third weapon, one that kills slowly, from above, long after the wind has passed. It falls from the sky by the foot and it can bury an entire village in a single night. Some super typhoons kill you with wind, some kill you with the sea, and a few kill you with rain alone. The wind and surge are loud, fast and obvious, but a super typhoon carries a quieter weapon, just as deadly. Water falling from the sky, in amounts that sound impossible until you see what they do to a mountainside. A big storm is a machine for lifting ocean water into the air and dropping it back down as rain. The strongest ones can pour out staggering amounts. In the worst cases, a single storm dumps more than a yard of rain in a day or two, 3 feet of water falling on the same ground, faster than any river or drain can carry it away. Whole regions receive a year's worth of rain in a weekend. Where does that much water come from? Sometimes a storm taps into a river in the sky, a long ribbon of extremely moist air streaming in from far across the ocean. The storm grabs that ribbon and wrings it out over the land like a soaked towel twisted in a giant's hands. As long as the ribbon keeps feeding in, the rain keeps falling hour after hour with no sign of stopping. The clearest lesson came from a storm named Morakot, which struck Taiwan in 2009. Its wind was nothing special. Its rain was historic. Morakot crawled slowly over the island and unloaded an astonishing amount of water, close to 9 feet of rain over just a few days. That is a wall of water taller than most rooms, falling out of the sky onto steep green slopes. On saturated mountains, that much rain does something terrifying. The soil soaks up water until it can hold no more, and then entire hillsides simply let go. In the village of Xiaolin, tucked into the mountains, a massive landslide broke loose in the night. In moments, a wave of mud, rock, and shattered trees swept down and buried the village whole. Hundreds of people were lost beneath the earth while they slept. An entire community erased in a single night by rain. This is the hidden danger of a storm that moves slowly. A fast storm blows through and leaves. A slow storm parks over a region and rains and rains and rains. The longer it lingers, the more water it delivers, and the more the ground can take before it breaks. Sometimes the calm-looking, weaker storms cause the worst disasters simply because they refuse to leave, and rain reaches far beyond the coast. Wind and surge strike the shoreline, then fade. Rain rides the storm deep inland, over hills and valleys, dropping its load on towns that thought they were safely away from the sea. Flash floods roar down dry gullies, rivers burst their banks, bridges wash away. People hundreds of miles from the ocean drown in water the storm carried to them. Here is the trend that worries scientists now. A warmer world puts more moisture into the air. Warmer air holds more water, so today's storms arrive carrying heavier loads of rain than the storms of decades past. The same wind speed now comes with far more flooding behind it. The rain weapon is growing stronger even as the wind stays the same. So a super typhoon is really 3 storms in one: wind, surge, and flood. And just when you think you understand how one behaves, it does something that seems to break the rules, weakening and then healing itself right before your eyes. Sometimes a dying super typhoon does something that looks like a magic trick. It falls apart, then comes back stronger. By now you know, the eye wall is the storm's engine, the ring of fierce cloud where the winds blow hardest. A tight, small eye wall means a powerful storm, but the most intense storms have a strange habit. Right when they seem to be at their peak, they begin to take themselves apart and rebuild from the outside in. Here is what happens. Around the original eye wall, a second ring of thunderstorm starts to form, a wider circle out beyond the first. Now the storm has 2 eye walls, one inside the other, like a bullseye, and these 2 rings compete. The outer ring is bigger, and it starts stealing the warm, wet air that the inner ring needs to survive. Starved of its fuel, the inner eye wall weakens, chokes, and dies. For a while, this actually calms the storm. As the old eye wall crumbles, the top wind speeds drop. From the outside, it looks like the monster is finally fading, losing its punch. Coastal communities watching the numbers might feel a flicker of hope. That hope can be a trap, because the outer ring is now taking over. It tightens, shrinking inward toward the center, becoming the new eye wall, and as it contracts, it spins up. The same trick a skater uses when she pulls her arms in and whirls faster. Within hours, the storm can roar back to full strength, sometimes stronger than before, with a fresh, tight eye wall and renewed fury. Forecasters call this whole process an eye wall replacement, and it is one of the great wildcards in predicting these storms. The timing of it can decide everything. If a storm finishes rebuilding out at sea and then contracts to full power, just as it reaches the coast, it slams the shore at its worst. If instead it happens to be in the weak, in-between phase at landfall, caught with its old eye wall gone and its new one not yet spun up, a coastline can be spared the very worst blow, saved by luck and timing. This makes the forecaster's job even harder. A storm can grow and shrink and grow again on its own schedule, breathing in and out like some vast living thing. Predicting exactly when it will finish a rebuild and how strong it will be at that moment is one of the toughest calls in the science. Some storms take this to a bizarre extreme. A few powerful typhoons have formed 3 eye walls at once, rings within rings within rings. One famous storm carried a triple set of eye walls as it approached land. It began an eye wall replacement but ran out of time before finishing it, and weakened gradually in its final hours. That slow fade likely spared the coast a far worse disaster, a rare gift of timing. For the people watching from the shore, all of this feels like cruel unpredictability. The storm looks like it is weakening, so they let their guard down. Then it heals and returns, hitting harder than the forecast that morning suggested. A super typhoon can lie about its own strength right up until the moment it arrives, so these giants can grow, kill 3 different ways, and even rebuild themselves. It raises an obvious question. Just how big can one of these storms get? The answer is a monster so large it once covered nearly half a continent, a storm that still holds records no other has ever touched. In the autumn of 1979, a storm grew so large it would have covered nearly half of the United States. Its name was Tip, and to this day, it holds the record as the biggest tropical storm ever measured on our planet. We have talked about super typhoons being wide. Tip redefined the word. Its swirling wind field stretched about 1,380 miles from one side to the other. Laid over a map of America, a storm that size would reach from the west coast almost to the Mississippi River, a single spinning system blanketing half the country at once. Try to picture that. If Tip's center sat over Kansas, its outer winds would be brushing California on one side and the Great Lakes on the other. Planes would have to fly for hours just to cross from one edge of the storm to the other. No storm before or since has ever grown so large. Tip was born in the Western Pacific and, like all these giants, fed on warm ocean water. Rather than staying compact, it spread outward as it strengthened, its circulation ballooning wider and wider until it was nearly twice the size of an average typhoon. It passed near the island of Guam and swept across huge stretches of open sea, a storm so vast that ships hundreds of miles apart were all caught in the same system. Here is something that surprises people. A giant storm can have a tiny eye. Even at its record-breaking size, Tip's calm central eye was only about 10 miles across, a small quiet dot at the heart of a storm wider than most countries. The size of a typhoon and the size of its eye are two different things. You can have an enormous storm wrapped around a small, tight centre, and often that is exactly what the strongest ones look like. Why does sheer size matter so much? Because a bigger storm is dangerous in ways a small one can never be. It batters a coastline for far longer, since it takes many more hours for that huge body to pass over you. It piles up a wider, more powerful storm surge because its winds push on a larger stretch of ocean at once, and it spreads its rain, wind and flooding across a vastly greater area, threatening many more towns in a single strike. A small fierce storm hits like a punch. A giant like Tip lands like a slow crushing weight. Luckily for us, Tip stayed over the ocean for most of its life and weakened before reaching heavily populated land, so its human toll stayed far lower than its size might suggest. Had a monster that large struck a crowded coastline at full strength, the disaster would have been almost beyond imagining. Tip is a warning written across the record books, a glimpse of just how large these engines of wind can grow when the ocean feeds them enough. And the size was only one of the records Tip set that autumn. Deep at its centre, something else was happening, a measurement that told scientists this was the most powerful storm they had ever seen. It went beyond wind speed or width. It came down to a single number, a reading of the air itself, and it dropped lower than any reading ever taken anywhere on the surface of the Earth. That number is the truest measure of a storm's raw power, and Tip still stands today as the deepest, darkest record of them all. The true strength of a storm is hidden in a number you cannot feel, and Tip's number is the most extreme ever recorded. All this time we have measured storms by their wind. But wind is really just a symptom. The deeper truth about a storm's power lives in something called air pressure, the weight of the atmosphere pressing down from above. And at the heart of a super typhoon, that pressure drops to almost unbelievable lows. Let me explain pressure simply. All around you, right now, air is pushing on your body from every direction. You barely notice it, because you have felt it your whole life. That push is air pressure. In a storm, the air at the centre gets pulled upward and away so fiercely that far less of it is left pressing down. The centre becomes a deep well of low pressure, a hole in the weight of the sky. Here is the key rule that forecasters live by. The lower the pressure at a storm's centre, the stronger the storm. A deep pressure drop means air is rushing in from the sides with tremendous force to fill the gap, and that rushing air is the wind. So when scientists want to know how powerful a storm truly is, they look past the wind to the pressure, because pressure reveals the raw engine behind everything else. Normal air pressure at sea level sits around 1013 on the scale meteorologists use. A strong typhoon might drop to 920 or 900. That is already a monster. Then there is Tip. At its peak, Tip's central pressure fell to about 870, the lowest sea level pressure ever recorded anywhere on Earth. No storm on record has ever gone deeper. That single reading is why scientists call Tip the most intense storm in history. Its enormous size was one record. This bottomless pressure was another, and in many ways the more important one. It meant the engine at Tip's core was running harder than any storm engine ever measured, pulling the sky down into itself with unmatched force. Think of pressure as the depth of a whirlpool. A shallow dip in the water barely tugs at a passing leaf. A deep, dark funnel drags everything nearby spiraling down into it. A storm's low pressure works the same way, except it pulls air instead of water. Tip carved the deepest such whirlpool in the atmosphere that humans have ever seen, and everything around it, all that record wind and size, was the sky pouring in toward that hole. This is why forecasters watch pressure so closely today. When they see the central pressure of a storm falling fast, they know its winds are about to catch up. A plunging pressure reading is often the first sign that a storm is entering that violent leap. The rapid strengthening we met earlier, before the wind gauges even show it. Pressure is the early warning hidden inside the machine, and here is the sobering thought. Tip set its record back in 1979, in a cooler world than the one we live in now. The oceans today hold more heat than they did then, more fuel for these engines to burn. Scientists wonder whether a storm could someday go even deeper than Tip, or whether the record that has stood for decades might one day fall, because the ocean that builds these monsters is changing, and the question of how strong a typhoon could truly become is one we are only beginning to answer. Every engine has a top speed, and so does a storm. Your car cannot go faster than a certain point, no matter how hard you press the gas. The engine simply runs out of room to push. A super typhoon works the same way. There is a ceiling on how strong it can grow, a limit set by the temperature of the ocean beneath it. Scientists call it the maximum potential intensity, the fastest a storm's winds could ever possibly blow in a given patch of sea and sky. A scientist at the Massachusetts Institute of Technology worked out the math for this back in the 1980s. His idea was simple and powerful. Since a storm is a heat engine running on the warmth of the ocean, its strength is capped by how much heat that ocean can offer. Warm water, higher ceiling. Cool water, lower ceiling. Feed the engine more heat, and it can rev higher before it maxes out. So how high is the ceiling? For most of the tropical ocean today, the top speed works out to somewhere around 200 miles an hour of sustained wind. That is the theoretical fastest a storm could blow given the water we have now. A wall of wind at 200 miles an hour, faster than a Formula One car at full throttle, stretched across miles of coastline. Very few storms ever reach their ceiling. Most fall short, tripped up by dry air, wind shear, or simply running out of ocean before they max out. But a rare few come frighteningly close. In 2015, a storm named Patricia, off the coast of Mexico, wound its winds up to around 215 miles an hour, the strongest winds ever measured in any storm on Earth. It formed over water that was almost bathwater warm, and it climbed nearly to the very top of what the ocean allowed. Here is the part that should give you pause. The ceiling moves, it rises as the ocean warms. Every extra degree of heat in the sea lifts the speed limit a little higher, giving future storms more room to grow. The same scientists showed that a warming world would raise the maximum strength a storm could reach. We are slowly building a taller ceiling for the monster to climb toward, and there is a cruel twist in the numbers. The jump from a strong storm to a record one may look small on paper, but the damage climbs far more steeply than the wind. Push the top winds from around 180 up to 215 miles an hour, and the destruction roughly quadruples. A small climb in wind speed can mean 4 times the ruin. Some storms even briefly break their own speed limit. Scientists call this superintensity, when a storm finds a little extra energy hidden in its core and pushes past the ceiling the theory predicts. It is rare, and it never lasts long. But it hints that these engines still hold secrets we have not fully mapped. So there is a limit, and the ocean is slowly raising it, year by warming year. But a storm cannot grow at all without one more ingredient, a hidden ingredient it borrows from the spin of the planet itself. And there is one place on Earth where that ingredient runs out completely, a place where, by all the rules, these monsters should never be able to form. Storms borrow their spin from the whole spinning planet, and there is one line on the map where that borrowing becomes impossible. We have talked about warm water and calm winds, but a storm needs one more thing to organize, something easy to overlook. It needs to rotate. A super typhoon is a giant spinning wheel of cloud, and that spin has to start somewhere. It comes from the Earth itself, turning beneath the storm as our planet rotates once a day. Here is the strange part. That helping spin is strong near the poles and fades to nothing at the equator. Right along the middle of the Earth, the turning of the planet gives a storm almost no twist to work with. So storms almost never form in that narrow band, roughly 300 miles on either side of the equator. It is one of the few safe stripes on the tropical map, a place where the ocean can be blazing hot and still refuse to spin up a monster. Most typhoons obey this rule. They form a comfortable distance from the equator, where the planet's spin can give them a good push, then curve away toward higher latitudes as they grow. Forecasters count on it. It is one of the few things about these storms they can almost take for granted. Almost. Because every so often, a storm breaks the rule, and those are some of the scariest of all. Remember Haiyan, the storm that flattened Tacloban? It was born unusually close to the equator, far nearer that forbidden band than most storms dare to form. It should have struggled to spin up at all. Instead, it found a rare pocket of just enough twist, grabbed onto the deep warm water below, and exploded into the strongest landfalling storm ever recorded. The rule breaker became the record holder. Why does a low birthplace make a storm more dangerous? 2 reasons. First, a storm forming close to the equator often starts its life pointed almost straight west, with a long clear runway of warm ocean ahead and no land to slow it down. It can strengthen the entire way. Second, storms that form that far south tend to arrive at places less used to them, catching people who have fewer defences and less practice getting out of the way. There is a deeper worry hiding here. The exact size of that calm equatorial band is tied to the climate. As the planet warms, the whole tropical zone appears to be widening, stretching farther north and south. If the region where storms can form spreads with it, the map of danger changes. Coastlines that once sat just outside the reach of these monsters could find themselves inside it. For now, the rule mostly holds. Storms keep their distance from the equator, and forecasters keep drawing their tracks with that in mind. But the exceptions, the rare rule breakers like Haiyan, are a reminder that these storms do not always play by the patterns we expect. And this year, the Western Pacific has been throwing the pattern out the window entirely. The ocean out there is running so hot and churning out so many storms that forecasters are watching a season unlike almost any they have seen before. The numbers behind it are staggering. This year, the Western Pacific has been running a fever, and the numbers tell a frightening story. Every storm season has a rhythm. Some quiet years bring only a handful of weak systems. Some busy years spawn a long line of powerful ones. Forecasters have a way to measure the overall punch of a whole season, adding up the strength of every storm and how long each one lasts. They call it accumulated cyclone energy. Think of it as the total horsepower of an entire season, rolled into one number. By that measure, 2026 has been off the charts. Partway through the year, the Western Pacific had already piled up more than double its usual storm energy for that point in the season. Double. The ocean out there produced storms in bunches, and it produced them bigger, stronger, and more often than the calendar said it should. Why so violent a year? Everything we have talked about, arriving at once, across a huge stretch of sea. The water has been unusually warm at the surface and warm far below, that deep heat acting like a stack of dry logs. On top of that, patterns in the ocean and atmosphere have kept the high-altitude winds calmer than normal over wide areas, taking the brake off again and again, fuel loaded, brake released, repeat for months. The result has been a parade. Storm after storm winding up over that superheated water, several of them climbing all the way to super typhoon strength. Some reach the very top rank, the same rank as the worst hurricanes to ever strike the United States. And they kept coming. One fading as the next was already forming behind it. This matters far beyond a line on a chart. A busy, violent season means more chances for one of these monsters to find a coastline full of people. It means rescue crews and hospitals and shelters getting hit again and again, with little time to recover between blows. A single super typhoon is a disaster. A season stacked with them is a slow siege. It also fits a pattern that scientists have been warning about for years. The total number of storms each year may hold steady, or even drop slightly. but the share of them that grow into the most violent top-tier monsters appears to be climbing. Fewer weak storms, more terrifying ones. A season like this one, packed with giants, is exactly what that warning looks like when it comes true, and here is the part that keeps forecasters uneasy even now. Storm seasons in this part of the world often peak in late summer and early fall, so a year that is already breaking energy records may have its worst chapters still ahead, more monsters waiting in the warm water, ready to spin up before the season finally winds down. For the millions of people who live along these coasts, from the Philippines to Japan to the coast of China, a season like this is a long stretch of held breath, watching the forecasts, wondering which storm will be the one that turns toward home. Some of this year's storms have already earned their place in the record books. To understand what this fever of a season really means, it helps to meet a few of the monsters it has produced. Give a season this much fuel, and it starts building monsters one after another. Early in the year, before the season had even hit its usual stride, a storm named Sinlaku wound up near the island of Guam and did something rare. It rocketed to the very top rank, with winds around 185 miles an hour, one of the earliest storms of its kind anyone could remember. A top-tier monster, months ahead of schedule, as if the ocean could not wait for summer to start. Then came Bavi, the storm we met earlier, exploding over water near 90 degrees Fahrenheit. Bavi climbed into the top rank too, its winds surging so fast in a single day that it became a textbook example of the violent leap. It tracked west toward Taiwan and China, the third top-tier monster of the year before the season had even peaked, and then Dolphin. This one hit home for millions. Dolphin blew up from a weak tropical storm into a full super typhoon in barely 2 days. That same terrifying speed we keep circling back to. At its peak, its winds screamed to around 165 miles an hour. It roared past the islands of southern Japan, where the wind howled through towns and military bases ordered everyone to stay indoors. Then it swung toward the coast of China, forcing fishing fleets into harbour and driving huge crowds of people inland, away from the water. 3 storms, 3 monsters, and those were only the loudest names in a season crowded with them. Picture a factory that keeps stamping out the same terrifying product, over and over, each one aimed at a different stretch of coast. That is what a superheated ocean does when nothing stands in its way. Here is what unsettles forecasters when they look at this lineup. It is the speed. Sinlaku, Bavi, and Dolphin all shared one trait. They strengthened fast, some of them explosively in a matter of days or even hours. This was a season of fast, explosive storms, the kind that appear almost out of nowhere and detonate. The very behaviour that is hardest to predict became the theme of the year. For the people in their paths, that speed changes everything. A storm that takes a week to build gives families time to think, to pack, to leave calmly. A storm that goes from harmless to catastrophic over a weekend forces snap decisions in the dark, with the water already rising. This year handed coastal communities that harder version again and again. And notice where these storms went. They marched straight towards some of the most crowded coastlines on the planet, where tens of millions of people live within reach of the water. Every one of these monsters was a near miss, or a direct hit for somebody. Everyone sent families scrambling. So this is the shape of the threat right now, a hotter ocean, a faster trigger, and coastlines packed with people. Put those together and you get exactly the kind of storm that forecasters lose sleep over, the one specific behaviour that turns a bad storm into a deadly surprise. It is time to look straight at that behaviour, the single scariest trick these storms have learned, the one that steals your warning time when you need it most. The scariest thing a storm can do is wait until the last minute to explode. We have met rapid intensification, the violent leap where a storm's winds jump by tens of miles an hour in a single day. On its own, that is frightening enough. But there is a version of it the forecasters fear above all others. It happens when a storm makes that leap right as it reaches the coast, exploding in the final hours before landfall, when there is almost no time left to react. Picture the timeline. In a normal case, a storm strengthens far out at sea, days before it arrives. Forecasters see it grow. Warnings go out. People board up, pack the car, and drive to higher ground with time to spare. The system works because the storm shows its cards early. Now change one thing. Suppose the storm stays weak and unremarkable until it is almost on top of the coast, then detonates in the last day, or even the last few hours. A moderate storm that everyone expected to ride out at home suddenly becomes a top-tier monster, and it is already at the doorstep. The warning that should have come days ago now comes with the wind already howling. Families who plan to shelter in place are trapped by a storm far stronger than the one they prepared for. This is the nightmare scenario, and it is becoming more common. Warmer, deeper ocean water reaches closer to shore than it used to, giving storms fuel to burn right up to the final moment. More and more, storms are saving their biggest leap for the end, blowing up near land where the water is warmest and the people are closest. The danger comes down to a single, shrinking resource: time. Everything that saves lives in a storm depends on warning time. Time to issue the alert. Time for people to hear it and believe it. Time to move the elderly, the sick, the children, the ones who cannot just jump in a car and go. A late-blooming storm steals every bit of that. It compresses a multi-day emergency into a few frantic hours, and the forecast struggles most at exactly this moment. Remember that the violent leap is the hardest thing to predict in all of storm science, so the storms that explode at the last second are also the ones the forecast is most likely to get wrong. The deadliest timing and the biggest forecast error land together right when people have the least room to recover from a mistake. Emergency planners have a brutal math problem because of this. Call for an evacuation too early based on a storm that might not blow up, and you risk moving millions of people for nothing, wearing out their trust for next time. Wait for certainty, and the storm may explode before everyone is clear. Every choice is a gamble against a storm that hides its strength until the last possible moment. So the whole game comes down to seeing the leap coming. If forecasters could reliably spot a last-minute explosion a day or two ahead, they could win back the warning time these storms try to steal. Which raises the obvious question: how do you watch a monster that lives hundreds of miles out at sea? The tools scientists use to hunt these storms are stranger and braver than you might imagine. In 1943, a pilot flew a small plane straight into a hurricane on a dare. It started as an argument on the ground in Texas. Other pilots doubted his aircraft could survive a hurricane's winds, so he took off, aimed for the storm, and punched right through its violent core to prove them wrong. He came back alive. And without meaning to, he had invented one of the most daring jobs in all of science, flying into the monster on purpose. Today those flights are careful missions, flown by crews known as hurricane hunters. Their planes are flying laboratories, packed with instruments, built to take a beating. A hurricane hunter aircraft flies a strange pattern across a storm, punching through the eye wall into the calm eye, crossing to the other side, punching back out, then repeating from a new angle, cutting the storm like slicing a pie, over and over, gathering numbers no satellite can capture. The star tool is a small tube called a drop sonde. The crew releases it from the belly of the plane, and it falls through the storm on a tiny parachute, beaming back readings several times every second the whole way down. As it drops, it measures the pressure, temperature, moisture, and wind at every level, from high in the clouds all the way to the ocean surface. Each one is a tiny weather station on a wire, taking the storm's pulse from the inside. Why go to all this trouble and risk when we have satellites watching from space? Because a satellite sees only the outside. It stares down at the swirl of clouds and makes an educated guess about what is happening underneath. That guess is good, though it can be off by a lot. Only a plane flying inside can measure the one number that reveals a storm's true strength, the air pressure deep at its core, the reading that defines the real power of the beast. Here is a hard truth about the Western Pacific, though. Almost no one flies into these typhoons. The routine hurricane hunter flights mostly cover storms threatening the United States. For the crowded coastlines of Asia, where the strongest storms on Earth spin up, forecasters usually have to rely on eyes in the sky alone. So they lean on a clever trick invented in the 1970s. Scientists learned to read a storm's strength from the shape and pattern of its clouds in satellite pictures. A tight, round eye wrapped in cold, high cloud tops means a powerful storm. A ragged, lopsided swirl means a weaker one. It works like a doctor reading an X-ray, judging what is happening inside from the pattern on the outside. Skilled, yet never as sure as a hand on the pulse. That gap is exactly why the strongest typhoons are so often the hardest to measure in real time. The very storms that matter most, over the busiest coasts, are the ones we most often have to judge from far away. A storm can be a little stronger, or exploding a little faster than the satellite lets on. And even when the measurements are perfect, one enormous challenge remains. Knowing how strong a storm is right now is only half the battle. You still have to predict where it will be tomorrow, and drawing that future onto a map hides a trap that has fooled people again and again. On every storm map there is a cone spreading out ahead of the swirl, and most people read it completely wrong. When forecasters predict a storm's path, they draw a line for where the centre is most likely to go. Then they wrap that line in a widening shape, narrow near the storm and fanning out into the future. People call it the cone of uncertainty. It is one of the most useful and most misunderstood pictures in all of weather. Here is what the cone really means. Forecasters cannot pin down a storm's exact path days ahead, so the cone shows the range of places the centre might reasonably end up. It is narrow up close, because the near future is easier to call. It flares wide far out, because small errors early on grow into big ones over time. A tiny wobble today becomes a 100-mile difference in 3 days. Now, the trap. Most people look at the cone and think the danger stays inside those lines. The truth is far wider. The cone only shows where the centre of the storm might travel. A super typhoon can be hundreds of miles across, so its wind, rain and surge spill far outside the cone on every side. Whole regions that sit well beyond the lines can still be hammered. The cone traces the path of the eye, while the storm itself reaches much farther. Why does a small track error matter so much? Because which way the eye passes changes everything. If the centre comes ashore just to one side of a city, that city may catch the weaker half of the storm and survive with bruises. If it passes on the other side, the same city takes the ferocious half, with the strongest winds and the higher surge stacked right on top of it. A shift of only 20 or 30 miles, well within the normal margin of error, can be the difference between a scare and a catastrophe. This is the daily agony of a forecaster's job. They know the storm is coming, they know roughly where. But that last little bit of wobble, the part no one can predict perfectly, decides who gets the killing blow. Warn everyone in the wide cone, and you may move millions who end up barely touched. Warn only the most likely spot, and you may miss the people the storm actually hits. And remember, the cone only covers the path. It says nothing about how strong the storm will be when it arrives. Layer the intensity guesswork on top of the track guesswork, and the uncertainty doubles. A storm could be 20 miles off from the forecast track and also far stronger than expected. 2 errors combining into one nasty surprise for whoever lies beneath it. For the people watching the map at home, the lesson is simple and life-saving. If you can see your town anywhere near that cone, you are in the game. The lines are a best guess. Treat the whole area around them as live. The storm does not read the forecast, and it feels no need to stay inside the shape drawn for it. So forecasters keep chasing that last bit of certainty, hunting for any way to shrink the cone and sharpen the strength forecast. And lately, they have found a surprising new ally in that hunt, one that learns the habits of storms in a way no human ever could. The newest weapon against these storms is a machine that has studied thousands of storms and learned their habits. For decades, forecasting worked one way. Scientists wrote down the laws of physics that govern air and water, fed them into powerful computers, and let the machines calculate how a storm would move and grow. This approach transformed forecasting and saved countless lives. But it has always stumbled on the same wall, the sudden, violent leap in strength that hides in the tiny core of a storm. Now a different kind of tool has arrived. Instead of being handed the laws of physics, these new systems learn by example. Scientists feed them the records of thousands of past storms, every track, every burst of strengthening, every collapse, and the machine hunts for hidden patterns humans might miss. It is closer to how a veteran fisherman reads the sky, working from a lifetime of watching 10,000 storms and feeling in his gut what comes next. This year, researchers in China switched on a system built for exactly the problem that scares forecasters most. Its one job is to predict the violent leap, the rapid strengthening, up to a full day before it happens. Spotting that explosion coming even a single day early could hand a threatened coastline back the warning time these storms love to steal. In a country that decided this was one of its top scientific challenges, that is a serious bet on a serious problem, and the trend is spreading. Around the world, these learning machines are being aimed at storms, chewing through decades of data to sharpen both the track and the strength forecast. Some can sketch out a storm's likely future in seconds, work that once took the biggest supercomputers hours to grind through. Faster forecasts mean more time for people to act. It would be a mistake, though, to think the problem is solved. These systems are powerful, and they are still young. A machine that learns only from the past can be caught off guard by something new, and a warming ocean is busy building storms unlike the ones in the record books. The machine has never seen a storm quite like the ones the future is preparing, so it can be fooled exactly when we need it most. The best forecasters know this, so they treat the machine as one voice among many. They weigh its guess against the physics models, against the satellite pictures, against their own hard-earned instinct. When all of those point the same way, confidence grows. When they disagree, the humans lean in and think harder. The machine is a brilliant new tool, and a tool still needs a skilled hand to guide it. The goal behind all of it is the same one that has driven this science from the start. Buy people time. Every hour of extra warning is a family that gets out, a hospital that moves its patients, a town that boards up before the wind arrives. The whole towering effort of satellites, hurricane hunters, physics models, and learning machines comes down to that single human prize. A little more time, because here is the truth we keep circling back to. The storms are changing faster than our tools can fully keep up. The ocean that builds them is warming, and a warmer sea does more than strengthen a single storm. It quietly changes the rules for all of them. The ocean has been quietly swallowing almost all the extra heat trapped around our planet, and that heat is going straight into the storms. When people picture a warming world, they think of hot air, but the air holds only a sliver of the extra warmth. The vast majority of it, more than 9 parts out of 10, has sunk into the sea. The ocean is a giant heat sponge, and it has been soaking up the heat for decades, growing warmer year after year, deeper and deeper down. For a super typhoon, that is like refilling the fuel tank and then making it bigger. We already saw that these storms run on ocean warmth, and that the deep heat matters as much as the surface. A hotter, deeper ocean hands them more fuel to burn, longer runs of it, and fewer cold patches to slow them down. The sea is stacking the deck in the monster's favour. Watch how it changes each part of the threat. First, the ceiling rises. That top speed a storm can reach, set by the warmth below it, climbs as the water heats. The strongest storms of the future have room to grow stronger than the strongest of the past. Second, the violent leap gets easier. With deep warmth everywhere, more storms find the fuel to explode, and rapid intensification happens far more often than it once did, roughly 3 times as often as decades ago. None of this means every storm becomes a monster. Most storms still fizzle, torn apart by dry air or high winds, same as always. The change is in the odds. On a hotter ocean, when a storm does find its window, it can go further, faster, and higher than it could have a generation ago. The dice are the same. The sea has quietly weighted them, loaded now in the monster's favour. And the trend points one direction. Scientists expect the total number of storms each year to hold roughly steady, or even dip a little. But the share that reached the top most violent ranks is climbing. A world with fewer weak storms and more giant ones is the future the warming ocean is building, and this year's crowded, ferocious season is a preview of it. Here is the part that makes it feel so relentless. The ocean is slow to heat, and it is just as slow to cool. All that warmth stored in the deep sea will stay there for a very long time, no matter what we do next. The fuel is already loaded for storms that have not even formed yet, for seasons still years away. We have set the table for monsters we will never see coming. That does not make the future hopeless. The amount of extra heat we keep adding still shapes how far this goes, how high that ceiling climbs, how often these leaps happen, the choices ahead still bend the curve, but the ocean has already changed enough to reshape the storms we live with right now, today, in ways we are only starting to measure. And the warming does something beyond making the wind blow harder. It reaches into the sky and changes the rain, loading every future storm with a heavier, deadlier flood than the storms our grandparents knew. Warm air is thirsty for water, and that one simple fact is turning every future storm into a heavier flood. There is a basic rule of the sky that scientists have known for a long time. Warmer air can hold more moisture. For every degree the air heats up, it can carry a little more water vapour, invisibly, until a storm wrings it out as rain. It is a small percentage per degree, but over a whole warming planet it adds up to a stunning amount of extra water hanging in the air, waiting to fall. A super typhoon is a machine for grabbing that airborne water and dumping it. So when the air is warmer and wetter, the storm has more to dump. Scientists estimate that storms in today's warmed-up world are already producing something like 30% heavier rainfall than they would have in a cooler past. 30% more water falling on the same towns, in the same few hours, with the same old drains and rivers straining to carry it away. Sit with what that means on the ground. A storm no longer needs record-breaking wind to be a killer. Even a middling typhoon, with unremarkable wind speeds, can now unload a flood far worse than its wind would suggest. The wind gauge says ordinary, the rain gauge says disaster. Two storms with identical winds, one from decades ago and one from today, can leave behind very different amounts of drowned streets and buried hillsides. We already saw where this leads, with that slow storm that dropped nearly 9 feet of rain on the mountains and buried a village in the night. A warmer world makes those rain totals easier to reach and more common. The flood, which was always one of the storm's 3 weapons, is quietly becoming its sharpest, and rain is a sneaky killer. Wind and surge announce themselves. You can see the sky darken and the sea rise. Rain flooding creeps up slowly, filling rivers hours after the storm has moved on, drowning towns far inland that thought the danger had passed. People let their guard down, and the water comes for them anyway, sometimes a full day later and 100 miles from the coast. There is a cruel pairing hidden in all this too. The same warm ocean that loads the storm with rain also tends to make it stronger and slower. A stronger storm pulls up more water vapour. A slower storm parks over one spot longer, giving all that rain more time to pile up in the same place. Warmer, wetter and slower, all feeding each other, all pushing the rain totals higher. For cities, this rewrites the risk. Drainage systems, dams and flood walls were built for the storms of the past, sized for rainfall that once counted as extreme. Now that old extreme is becoming the new normal, and the defences are quietly falling behind. A pipe built to handle the worst storm of 1980 may simply overflow when today's wetter monster arrives. So the wind is climbing, and the rain is climbing with it. On their own, each is dangerous. What worries forecasters even more is where these growing storms are choosing to go, because the monsters are on the move, drifting toward coastlines that were never built to face them. The strongest storms are slowly drifting away from the equator, toward places that never expected to face them. For a long time, the map of typhoon danger stayed fairly fixed. Certain tropical coastlines, close to the warm heart of the ocean, took the worst hits year after year. They knew it. They built for it. Farther from the equator, in cooler, higher latitudes, big storms were rarer and usually weaker by the time they arrived. That was the deal, and it held for generations. That deal is changing. When scientists tracked where storms around the world reached their peak strength, they found the spot creeping steadily away from the equator. In both halves of the planet, the point of maximum fury has been shifting toward the poles at a rate of roughly 35 miles every 10 years. Over the past few decades, that adds up to a real and measurable march, storms hitting their hardest farther from the tropics than they used to. 35 miles a decade may sound slow. Over a human lifetime, it is enormous. It means coastlines that once sat safely outside the worst of the danger are gradually sliding into it. Cities that saw a monster storm once a century may start seeing them far more often. And these are places with a dangerous disadvantage, because they were never built for it. Think about what that means for a city unprepared. A coastline used to fierce typhoons has seawalls, strict building codes, evacuation plans, and people who have lived through storms and take the warnings seriously. A coastline that has rarely felt a strong storm has weaker buildings, thinner defences, and residents who may not grasp the danger until it is on top of them. The same storm that a hardened coast shrugs off can devastate one caught off guard. Why are the storms migrating? It traces back to the warming we have been following. As the planet heats, the wide belt of the tropics appears to be expanding, stretching farther north and south. The conditions that let storms grow strong, the warm water and the calm high winds are spreading with it, opening new territory for these monsters at higher latitudes. The zone of danger is widening along with the tropics themselves. This does not fall evenly across the globe. The shift shows up most clearly in the Pacific, the very ocean that breeds the strongest storms on Earth. So the change is hitting hardest exactly where the biggest monsters live, pushing top-tier typhoons toward crowded coasts that sit north of the usual strike zone. There is a second edge to this too. As the storms drift poleward, some regions closer to the equator may see fewer of them. That sounds like good news, until you remember that many of those places depend on storm rains to fill their rivers and reservoirs. Lose the storms, and you may lose the water they bring, trading one disaster for another. So the danger keeps growing, and it keeps moving, spreading into new lands and pulling back from old ones, redrawing the map that coastal cities have trusted for centuries. And when one of these wandering giants finally strikes an unready coast, it rarely arrives with a single weapon. It brings all of them at once. A super typhoon rarely kills with a single weapon. It attacks with all of them at once, and that is what breaks a city. Through this story, we have met the storm's arsenal one piece at a time. The screaming wind of the eye wall, the wall of seawater in the surge, the drowning flood of the rain. On their own, each is a serious disaster. The true horror comes when they all arrive together, in the same hours, layered on top of one another. Picture the worst moment of a landfall. The eye wall roars in, wind strong enough to tear roofs away and turn debris into missiles. At that exact moment, the surge shoves the ocean inland, filling streets and homes with rising water, and soaking through all of it, the rain pours down by the foot, swelling rivers and flooding everything the sea has not already claimed. 3 catastrophes stacked into one, striking the same neighbourhood in the same terrible window. Each hazard makes the others deadlier. Try to flee the rising surge, and the wind is too strong to stand in. Climb to your roof to escape the flood, and you're exposed to flying debris. Every safe move against one weapon puts you in the path of another. The storm closes every door at once, and the damage cascades. The wind snaps the power lines, so the lights go out and the pumps that fight flooding stop working. The surge blocks the roads, so rescue trucks cannot get through. The rain washes out the bridges, so whole towns are cut off. One failure triggers the next, and a modern city which runs on a web of connected systems comes apart thread by thread. Hospitals lose power in the dark, phones go silent. Help cannot reach the people who need it. This is what scientists mean when they warn about compound disasters. It is the reason a super typhoon can overwhelm even a well-prepared place. A city might defend against any one of these threats. Defending against all 3, striking together at full strength, is a far taller order. Each defense is built for its own emergency, and the storm attacks every emergency at the same time. The aftermath stretches the pain out for months. Once the wind dies and the water drains, the wreckage remains. No power, no clean water, roads buried, bridges gone, crops drowned in the fields. Disease spreads through flooded streets. Families who survive the storm itself now face weeks or months without the basics of daily life. The suffering carries on long after the storm has left. In many ways, it is just beginning, and a busy season makes it worse. When storm after storm slams the same region, as this year's fever of a season has done, there is no time to recover between blows. A coastline still cleaning up from one monster gets hit by the next, its defences already broken, its people already exhausted. The damage stacks, storm on storm, until whole regions are worn down. All of this destruction carries a staggering price, one measured in a currency beyond the human toll. When you add up what a single super typhoon can cost, the number climbs so high it can swallow the entire wealth a nation produces in a year. One super typhoon can cost more money than an entire country earns in a year. We measure these storms in lives, and we should. But there is another kind of wreckage they leave behind, a financial blow so large it can knock a nation off its feet for years. When the storm that flattened Tacloban finished its rampage, the bill for the damage came to around $14 billion. For the Philippines, that single storm wiped out an amount equal to more than 1/20th of everything the whole country produced that year. One storm, one morning, a single day of wind and water, leaving a wound that deep in the national wallet. Where does all that money go? Everywhere at once. Homes flattened by the thousands, each one a family that must rebuild from nothing. Roads, bridges, and ports torn apart, the very arteries a region needs to move goods and people. Power lines and water systems destroyed. Farms drowned and their crops lost, which means empty markets and hunger long after the wind is gone. Factories and shops wiped out, and with them, the jobs that let people recover. The storm breaks more than buildings. It breaks the machine of daily life, and the costs keep coming long after the skies clear. There is the emergency, the search and rescue, the shelters, the food and water flown in. Then the far bigger, slower cost of rebuilding, which can drag on for years. For a wealthy nation, a giant storm is a brutal expense. For a poorer one, it can erase decades of hard-won progress in a single day, pushing millions back into poverty they had climbed out of. Here is what makes the money problem worse over time. The coasts these storms hit are filling up with more people and more valuable things. Cities are growing along the shore. New buildings, new roads, new businesses crowd right up to the water. So every year there is more in harm's way, more that a storm can smash. Even if the storms themselves stayed exactly the same, the damage they cause would climb simply because we keep building more in their path. Now add the storms getting stronger and wetter, and the migration toward new coastlines, and you can see where the numbers are heading. Bigger monsters, hitting richer and more crowded coasts, some of them unprepared. The price tag of a bad storm season is climbing on two curves at once, the storms growing fiercer and the targets growing larger. There is a bitter unfairness woven through all of this. The countries that often take the hardest hits from these storms are frequently the ones with the least money to defend against them or bounce back afterward. A storm can cost a poor nation a fortune it never had, then leave it deeper in debt, more exposed and less able to survive the next one. The disaster becomes a trap that is hard to climb out of. Money, though, can be rebuilt. Buildings can rise again. The one loss that can never be undone is human, and that is where the hardest decisions of all get made, long before the storm arrives, when officials must look at a coming monster and choose whether to move millions of people out of its way. Imagine having to decide whether to move 1 million people out of a city, with only hours to make the call. This is the burden that falls on emergency officials when a super typhoon turns toward the coast. Everything we have covered, the fuel, the forecast, the cone, the shrinking warning time, all of it lands on one impossible human choice. When do you tell people to leave? And how do you move that many bodies out of the way of a monster before it arrives? Start with the sheer scale. The coasts these storms threaten are among the most crowded places on the planet. A single city in the path can hold millions. Moving even a fraction of them means clogged roads, packed trains and shelters filling to bursting. There are only so many ways out of a city, and a highway built for a normal rush hour cannot swallow 1 million cars fleeing at once. The escape route itself becomes a trap. Then there is the timing, and it is agony. Call the evacuation too early, before the forecast is sure, and you might empty a city for a storm that swerves away or fizzles out. Do that a few times and people stop believing the warnings. The next time you shout that a monster is coming, they shrug and stay home, remembering the last false alarm. Trust is a resource, and every wrong call spends some of it. But wait too long, and the storm may explode at the last minute, that late leap we saw, sealing the roads with wind and water before everyone is clear. People caught on a flooded highway in the open are in terrible danger, so officials are squeezed from both sides, move too soon and cry wolf, move too late and trap people in the storm. There is a narrow shifting window between, and they have to find it while the forecast is still uncertain, and not everyone can simply go. Think about who lives in a city. the elderly who cannot travel easily, hospital patients hooked to machines, families with no car and no money for a bus, people who cannot leave behind a sick relative, or who fear their home will be looted, or who have nowhere to go even if they flee. For many, the order to evacuate collides with the hard reality that leaving is nearly impossible. There is a quieter problem too, the one that haunted Tacloban. A warning only works if people truly picture the danger. Tell a community that survived many big winds to flee a storm surge, and some will stay, unable to imagine the sea rising above their rooftops. The words reach their ears without reaching their gut. Closing that gap between hearing a warning and feeling it is one of the hardest and most important jobs in disaster science. So the people who make these calls carry a weight most of us never feel. Guess right, and a city empties in time and the death toll stays low. Guess wrong in either direction, and people die, either trapped by the storm or lost in the chaos of a panicked, needless flight. They make that gamble with incomplete information, against a monster that hides its strength until the end. All of which leads to the question people always ask in the end. If these storms are so deadly, why can't we just stop them? Every few years someone suggests we should simply destroy a super typhoon before it hits. The idea always runs into the same wall. These storms are far too powerful to fight. Start with the raw energy. A mature super typhoon releases more heat energy in a single day than the entire world uses in electricity in a whole year. That is the scale of the beast. Any weapon we could throw at it, even the most powerful ones humans have ever built, is a pebble tossed at an avalanche. The storm would swallow it and keep spinning. People have seriously floated the wild ideas. Drop a nuclear bomb into the eye. Scientists have run the math, and it fails badly. The blast would add almost nothing to the storm's own vast energy, and it would spread deadly radiation across the ocean and downwind toward the very coast we were trying to protect. A catastrophe on top of a catastrophe. Others propose gentler tricks. Seed the clouds with chemicals to weaken the storm. Pour cold water or oil films over the sea to cut off its fuel. For decades, teams even flew into hurricanes to test cloud seeding directly. Every serious attempt ran into the same brutal truth. The storm is simply too big, too energetic, and too self-repairing. Poke it in one place, and it heals. We cannot outmuscle a machine that runs on an entire warm ocean. So the honest answer is that we cannot stop these storms, and we likely never will. That sounds bleak. It is where the hope begins. Because while we cannot beat the storm head-on, we have gotten remarkably good at surviving it. The real victory was always about getting out of its way. Look at what saves lives, and it is humble, unglamorous work. Warning systems that spot the storm days out and get the message to everyone in its path. Building codes that force homes and shelters to stand up to fierce wind. Seawalls and raised buildings that blunt the surge, and nature's own shield, the mangrove forests and coral reefs along a coast, which quietly break the force of the waves before they reach people. A thick belt of mangroves can soak up a storm surge like a giant sponge. The proof is in the numbers. Storms just as fierce as the deadliest ones in history now often kill far fewer people, because the warnings arrive earlier and the escapes are better planned. A super typhoon that once might have killed tens of thousands can, with good preparation, claim far fewer lives. The storm stayed just as fierce. We simply got smarter about surviving it. And that is the whole game now. We pour our effort into forecasting, into education, into stronger buildings and clearer warnings and protected coasts. Every one of those is a way of stealing back a little safety from a force we cannot defeat. We give up on stopping the monster and focus everything on outlasting it. But the challenge keeps growing, because the monster keeps growing. And that leaves us with one last sobering question, the one that quietly worries forecasters more than any other. The next great storm is already coming. What worries them is what it finds when it arrives. Somewhere over the warm Pacific, the next great storm is already taking its first breath. We have travelled the whole life of these monsters, from a quiet patch of warm sea to the strongest winds ever measured. From the calm lie of the eye to the wall of water that swallowed a city. Now we arrive at the question that sits behind all of it, the one that keeps forecasters staring at their screens late into the night. What happens when the next Haiyan arrives, and where will it choose to strike? Here is what they quietly brace for. A perfect, terrible alignment. A super typhoon that holds its full strength all the way to shore, a storm that makes its violent leap in the final hours, stealing the warning time, and a target that is new to this, a large, crowded, low-lying coastal city that has never truly faced a monster and is not built to survive one. Every ingredient for that nightmare is on the table right now. The ocean is hotter and deeper with heat than ever, raising the ceiling these storms can climb to. The violent leaps are happening more often, closer to land. The rain is heavier, the surge higher, the giants drifting toward coasts that were once out of reach, and the shores are packed with more people, and more that can be lost. We have built a world that is better at making these storms and more exposed to them at the same time. That is the fear, a Haiyan-scale storm aimed at a city of millions that never saw one coming. But this journey does not end in despair, because the same story holds the answer. We cannot stop these storms, yet we have learned to see them coming, to measure them, to warn against them, and to get out of their way. Every satellite watching from space, every plane flying into the eye, every learning machine hunting for the leap is a tool for buying the one thing that saves lives: time. The monster is enormous, and human cleverness has still managed to shrink its death toll again and again. So why should any of this matter to you, wherever you are? Because these storms are a warning written in wind and water, a preview of a planet whose oceans are changing under our hands. What the Pacific is doing now, other seas may do later. The lessons these coastlines are learning in blood and rebuilding are lessons for all of us, about how a warming world reshapes the very weather we live under. The Super Typhoon is the largest, most powerful storm engine on Earth. It runs on a warm ocean we are quietly making warmer. We cannot fight it. We can understand it, measure it, and outrun it. And every year the scientists who track these giants get a little sharper, a little faster, a little better at handing threatened families the warning they need. The next monster is out there, gathering its strength over the open sea. We cannot stop it from coming. What we can do is watch, and prepare, and be ready to move when it turns toward home. In the end, that is the whole story of humanity against the storm. We learn to survive it, one warning at a time,